Hello everyone, I am Suraj Balmekar, Assistant Professor of Mathematics at Ganpat Parsigar College of Education, and I welcome you to module number 9 of this course on elementary combinatorics titled The Binomial Theorem Part 1. In this module, we shall study the binomial theorem and some identities associated with it. Now, the binomial theorem is something that we are introduced to as early as in the 8th grade. If you recollect some identities of the form, say x plus y the whole squared equals x squared plus 2xy plus y squared. Then again we have x plus y the whole cubed, which is equal to x cubed plus 3x squared y plus 3xy squared plus y cubed, and so on and so forth. Meaning, if you take any positive integer n, you can expand what is x plus y raised to n. So in some sense, we have all been introduced to the binomial theorem, but not in the form that we will look at in this course. Alright? So, I'll just first read out the statement. The binomial theorem says that for all non-negative integers n, x plus y the whole raised to n is the sum of all combinations nck times x raised to k times y raised to n minus k. So if I have to expand x plus y the whole square in this manner, it will be 2c0 x raised to 0 y squared plus 2c1 x raised to 1 y raised to 1 plus 2c2 x raised to 2 y raised to 0, which if we simplify, 2c0 is 1, x raised to 0 is 1, this gives you y squared, 2c1 is 2, along with that you have x and y, and 2c2 is 1. So you get y squared plus 2xy plus x squared, which is what we know from here. X plus y the whole square equals x squared plus 2xy plus y squared. Now, this theorem can be proved using the principle of mathematical reduction, but since this is a combinatorial course, let us give a combinatorial argument for the proof of this theorem. Alright, so on the left hand side, I have x plus y the whole raised to n, which is nothing but x plus y into x plus y into x plus y times x plus y. We take this product n times. Now, if you have seen the previous examples, if you have observed what we did in case of x plus y the whole squared and x plus y the whole cubed, I'll just write them down again. You will notice that each term in this expansion is some combination of x and y. There is some power of x multiplied by some power of y, and there is some coefficient attached to that term. Now, let me take the example of x plus y the whole raised to cube so that you can understand the idea behind this proof. Now, in x plus y the whole cube, I have x plus y times x plus y times x plus y. Now, if I want to produce a term which contains only x in it and no y, I precisely have only one choice. That is, we choose x from this parenthesis, x from this parenthesis, and x from this parenthesis. So from three parentheses, I can choose one x each, okay, which means it becomes 3c3. I need to choose 3 x's. X raised to 3 and no y's, y raised to 0. This is the only way in which I can produce the x cubed term. Now, if I need to produce a term which contains 2 x's and 1 y, then I can choose two x's from the first and the second parenthesis and nothing from the third. I can choose two x's from the second and the third parenthesis and nothing from the first. And I can choose two x's from the first and the third parenthesis and nothing from the second. This is how I can go about it. So basically, from the three parentheses available to me, I can choose x from two of them. That will give me my x squared term, and of course from the third parenthesis I need to choose y. This is how I get my x squared y term. Similarly, if I have to choose one x, I will get 3c1, meaning from three parentheses I have to choose x from one parenthesis, x followed by y squared from the remaining two parentheses. And the last term would simply be 3c0 because I don't have to choose any x's from any of the parentheses. X raised to 0, y raised to 1. So this is the idea behind this proof. Since I have n parentheses with me, n brackets with me, and I have to choose a certain number of x's, the number of ways in which I can do this is nck. That is all basically. Alright, so let me formally write down this proof on the next slide. As mentioned earlier, each term in this expansion will contain some combination of x's and y's. In order to produce k x's, like mentioned earlier, if I want to produce a certain number of x's, k x's, and the remaining terms will of course contain all y's, which means n minus k y's, we can choose k x's from any of the n parentheses available to us. And this can be done in n, c, k ways. That is, the number of times x raised to k, y raised to n minus k appears in the expansion is nck. Therefore, we must have this expression, x plus y is to n should be equal to the term containing 0 x's and all n y's plus the term containing exactly 1 x and the remaining terms containing y, the remaining part of the product containing y, followed by 2 x's and the remainder of y, and we go on until I am left with all x's, that would be ncn, x raised to n, and no y's. Writing this in a very compact form, I get summation k goes from 0 to n, nck, x raised to k, y raised to n minus k. So this is how the proof of the binomial theorem goes about. This is a very nice combinatorial argument that we have given. Of course, as mentioned earlier, we can write down this proof using the principle of mathematical induction, but let us avoid it in this course, since this is an elementary course on combinatorics. Alright, moving on to the next theorem. For all positive integers n, the alternating sum of the binomial coefficients nck is 0. In other words, summation as k goes from 0 to n minus 1 raised to k times nck is 0. Just to give you an example at the start, suppose I take x plus y the whole cube. This will be x cube plus 3x squared y plus 3xy squared plus y cube. I now need to take the alternating sum. So I am basically taking minus 1 raised to 0 nc0 plus minus 1 raised to 1 nc1 plus minus 1 squared nc2 plus minus 1 cubed NC3. This gives me NC0, which is 1, minus 3 plus 3 minus 1. And this sum, as you can clearly see, comes to 0. So what this theorem basically tells me is that for every coefficient, the negative of that coefficient will also be present in my expansion. Alright, let us prove this here. The proof is very simple. From the binomial theorem, I have x plus y the whole raised to n is summation k goes from 0 to n, nck x raised to k, y raised to n minus k. Now if I take x is equal to minus 1 and y is equal to 1 and simply substitute in this expression, I get minus 1 plus 1 raised to n equals summation k goes from 0 to n, nck minus 1 raised to k, 1 raised to n minus k. The left hand side is simply 0, and on the right hand side I have nck minus 1 raised to k and 1 raised to a finite number. I don't know what is the value of n minus k, but for every single k this will be a finite value. And 1 raised to any finite positive integer is always 1. So this is 1. And I end up putting my result in this case. So a very simple proof using the binomial theorem. Something very similar is to be done in this theorem as well. I'll show you the shorter proof of this first, but I'll also show you a combinatorial argument to prove this identity. Now the shorter proof is very straightforward. Like in the previous theorem, we substituted x equal to 1, minus 1 and y equal to 1. Over here as well, I will substitute some specific values of x and y. So if you put x equal to 1 and y equal to 1 in the binomial theorem, we get 1 plus 1 the whole raised to n is equal to summation k goes from 0 to n, nck 1 raised to k, 1 raised to n minus k. Again, 1 raised to any finite positive integer is 1, which means we are left with only nck, and that's the end of the proof. This is the simplest way of proving this identity, by simply substituting x equal to 1 and y equal to 1. Now let us give a combinatorial argument for this proof. So let me say this is proof 1. Now let us do proof 2. Consider a set A containing n elements. If you have a set A containing n elements, from basic set theory we know that the power set of A contains 2 raised to n elements. If you look at the left hand side of my identity, it is 2 raised to n, which means it is counting the number of all possible subsets of A. The power set is nothing but the set of all subsets of A, which means that the left hand side of my identity is counting the number of subsets, which comes out to be 2 raised to n. I need to show that the right hand side also counts the same thing. Okay? Now for the right hand side, let us start with the smallest possible order of my subset. The number of subsets containing 0 elements will simply be nc0, which is 1. Basically, this is the empty set. The empty set is the subset of every single set, and it is the only set which contains 0 elements. Now, how do I form that? I have n elements, I am choosing nothing out of those n elements. So I get NC0 ways of forming a subset containing 0 elements. Let us continue. The number of subsets containing one element. In how many ways can I form singleton subsets of A? This is simply equal to the number of elements present in A. If I have n elements, I am choosing exactly one element out of those n. So the number of ways in which I can create singleton subsets is NC. Let us continue in this manner. If I want to find the number of subsets containing two elements, that will be equal to NC2. I have n elements, I choose any two out of those, I get NC2. And finally, continuing in this manner, the number of subsets containing n elements will simply be NCn, which will be the set A itself. It is the only set which contains all n elements. Now if you see, none of these cases overlap each other. In other words, there is no set which contains one element and at the same time it contains two elements. So these are all disjoint cases in simple words. Alright? Therefore, we must have 2 raised to n is equal to NC0 plus NC1 plus NC2 all the way up to NCn, since the cases are disjoint. And that's the proof of this identity. Alright, so we saw 2 ways of proving this identity, one using simple substitution and one where we used a proper combinatorial argument. This is another identity where we substitute specific values of x and y, but there's something more to be done in this case. Here I need to prove that summation as k goes from 1 to n, k and k is n times 2 raised to n minus 1. From the binomial theorem, I have x plus y raised to n equals summation k goes from 0 to n, nck, x raised to k, y raised to n minus k. If I put x equal to 1, we get, let me put y equal to 1 in the first case, let me put y equal to 1. I get x plus 1 the whole raised to n equals summation k goes from 0 to n, nck, x raised to k, 1 raised to n minus k. 1 raised to n minus k, as mentioned earlier, will always be 1. So this is what we end up getting finally. Now, differentiate this with respect to x. The right hand side is a finite sum, which means I can quite easily differentiate it. The derivative of the left hand side is n x plus 1 raised to n minus 1 times 1 using the product rule, using the chain rule. And on the right hand side, I get summation k x raised to k minus 1, but my index this time has to start from 1. And now all I need to do is substitute x equal to 1. Therefore, I get n. When x is 1, this becomes 2 raised to n minus 1. You get k equal to 1 in k times 1 raised to k minus 1 is 1 n c k. And that's the proof of the identity. Let us move on to the last proof in this module. It's called Pascal's identity. The identity says that for all non-negative integers n and k, the following identity holds. nck plus nck plus 1 equals n plus 1 ck plus 1. The proof of this is very interesting. It's simple as well. Very nice, lovely combinatorial argument. Again, we can give a proof for this using the definition of NCR or NCK and the properties of factorials. It can be done that way, but again, for the sake of this course, we use a combinatorial proof. Alright, the right hand side is n plus 1 ck plus 1. Now, the right hand side is telling me that I am selecting a committee of k plus 1 people from a set of n plus 1 people. So we can clearly write here that the right hand side is the number of ways of creating k plus 1 member committees from a group of n plus 1 people. This is pretty straightforward. Now, remember that we have a group of n plus 1 people. Suppose person A is a member of the group of n plus 1 people. So suppose we highlight a particular person A who is a part of this group of n plus 1 people. We can divide this problem now into two cases. Suppose the committee contains person A, then I will have a certain number of ways of forming such committees where person A is always a part of my committee. And the second case would be forming a committee where person A is not a member of the committee. Okay, so let me break it down into two cases. Case 1. Person A is a part of the committee. If person A is a part of the committee, that means one position out of those k plus 1 positions is fixed. It's gone to person A. I can't do anything about it. I need to now choose k more people because I have to form a committee of k plus 1. I need to choose k more people from a group of n people. I have n remaining people, I have to choose k more. In this case, one spot is reserved for person A and the remaining k people can be chosen in NCK ways from the group of the remaining n people. So this is one situation where person A is always a part of the committee. Now suppose I have the other scenario where person A is not a part of the committee. Now in this case, again since I am excluding person A from my committee, I have n people left to choose from. And I still need to choose k plus 1 people because this time No spot is being reserved for anybody. All k plus 1 spots are open, but I have only n people to choose from. So in this case, k plus 1 people can be chosen in n c k plus 1 ways from the group of n remaining people. Now again, like in the previous example where I showed you a combinatorial argument for 2 raised to n equals the sum of all the binomial coefficients, these two cases are also disjoint, meaning a person cannot be a part of the committee and not be a part of the committee at the same time. It's impossible. Which means whatever is counted on the left hand side is also counted by the right hand side. Since the cases are disjoint, we must have n plus 1 ck plus 1, which was my right hand side, equals nck plus nck plus 1. And again, these cases are exhaustive. There is no other case which you can create using the position of person A in the committee. He is either a part of the committee or he is not a part of the committee. So this is Pascal's identity using a combinatorial argument. Alright, in the next module we will see some more identities based on the binomial theorem. The references that we used for this module were Walk Through Combinatorics, a book by Nicholas Warner, and the book by Alan Lacker titled Applied Combinatorics.